So in this video, we will be learning how to get the energy available when you have a spontaneous redox reaction. So if you remember from the previous problems, this is 20.7, you have a positive voltage here. That means this reaction will be spontaneous. If it is spontaneous, then you will have some free energy given to you. So we can calculate that. So first, if you have a negative voltage, that means it is not spontaneous. And if you have a positive voltage, it will be spontaneous. So in terms of delta G, if it's spontaneous, you're going to have a negative delta G, and that is your energy that is free to be used. And then if it is negative, then you're going to have a positive delta G. Negative voltage, you'll have a positive delta G. Okay, so let's try a problem. So using the standard reduction potentials in table 20.1, determine whether the following reactions are spontaneous. So all you have to do is figure out whether the voltage is positive. So you need positive voltage for the reaction. For example, letter A. So for letter A, you're going from copper solid to copper plus 2. Here it is oxidized, so this is the anode. So copper is oxidized, giving away 2 electrons here. Okay, let's look at hydrogen here, H plus, 2H plus, becoming H2. You're going to put the electrons on the more positive side, 2 electrons here. Here, H plus gained electrons and it became reduced. So this is the cathode. To get the a cell potential, it is E cell is equal to E cat minus E anode. So all we have to do is look in the chart. I'm going to use table 20.1 for copper becoming copper plus 2. So it's up here. So there it is. For copper to become copper plus 2, so this is going backwards. So it's positive 0.34. So this is positive 0.34. Because it's going the opposite way, we're going to have to subtract it right here. Okay, so the anode is positive 0.34 volts. And when we reverse it, we're going to use the negative sign here. And then the cathode is being reduced, so it should be written like that. So it's right here. So it is 0. It is the standard cell. So the cell potential here is positive 0.34 volts. Because it's positive, that means it is spontaneous. Okay, please pause the video and do letter B on your own. I made a mistake. It's not positive. It is negative 0.34. Sorry. It's negative 0.34, so it is not spontaneous, as written here. So what you can do to make this spontaneous is flip it over to flip these products to that side. That will make it spontaneous. But as written, it is not spontaneous. Okay, so let's try letter B. The answer should be positive 0.83 volts. Okay, so let me work through it. Cl2 becoming 2Cl minus. Cl2 becoming 2Cl minus. It got more negative, so it's going to be reduced, and this is the cathode. And the electrons go on the more positive side, 2 electrons. Now 2I minus going to I2. So it became more positive, so it got oxidized and giving away 2 electrons. So this is the oxidation, this is the anode. Okay, so E cell is equal to E cat minus E anode. So the cathode is this one, so I have to look that up. what was it? Forgot. It is Cl2. Cl2 is here, positive 1.36. Minus the anode is this one right here. It's I minus and I2. So it's written here. It's written in reverse way, so it's going to be positive 0.54. Okay, since it's reversed, you take the negative of it. So it is positive 0.83 volts. Because it's positive, it is spontaneous. Now that you have the voltages, you can actually calculate the free energy. So free energy, remember, is delta G, and the formula is given here. Okay, so all you have to do is plug in the voltage that you get, the 0.83 volts right here. Okay, and then F is Faraday's constant. And Faraday's constant is the quantity of charge of 1 mole of electrons. Okay, I'll talk more about that in a few minutes. And then this is the number of electrons transferred. So for example, for this reaction, you took 2 electrons, this gave 2, so this N would be 2. Okay, so that would be 2. Faraday's constant, we're going to calculate that now. Okay, so it is the charge of a mole of electrons. So I'm thinking, well, that's easy. I know that Millikan found the charge of 1 electron, right? So all I have to do is multiply that by 6.022 E23, and that will give me the charge of a mole of electrons. Okay, so when I calculated that, I got, go ahead and plug that in the calculator. With 3 sig figs, I got 96,400. Okay, and the units would be, this is the unit of coulombs. Okay, this is the number of, okay, let me just write the units really quickly. Okay, so it is 1.60 E negative 19 coulombs for every 1 electron, and you have 6.022 E23 electrons inside 1 mole. So the unit would be 96,400 coulombs per moles of electrons. Okay. So this number you would have to remember, actually you don't have to, it's in the formula sheet. So if you look at your formula sheet here, here is Faraday's constant, 96,485 per mole of electrons. Okay, so I only had 3 sig figs, they have 1 to 5 sig figs. Okay. So this formula sheet also has the unit of a volt. Remember, the volt is how much energy you impart if you had 1 coulomb of charge going through. So if this is Faraday's constant, 96,485 coulombs per mole, we can change the units a little bit so it'll fit in the formula. So this formula says volt is equal to J over C. Solving for C, I'm going to put C on that side. CV is equal to J. So C is equal to divide V on both sides, J over V. So another way of writing this number is 96,485. Instead of C, you would write J over V mole. And you'll need that because the voltage will cancel when you multiply it by E in the formula when deriving the free energy. So the formula again is delta G is equal to negative NFE. Okay, so let's practice that. I'm going to skip the slide for now. I'll come back to it later. Let's do sample 20.10, letter A. So it says, using the standard reduction potential listed in table 20.1, calculate the standard free energy change. So they want delta G and the K equilibrium. We'll learn how to do that in a minute. We'll just do delta G for now at 298 for this reaction. So first, I have the formula delta G is equal to, what was it again? Negative NFE. Negative NFE. Okay, so now I just need N. To figure out N, I have to do the half reactions here. So I have 4Ag to 4Ag plus okay, I'm going to put the electrons on the more positive side, so I'm going to need 4 electrons to make this balance. Okay, then I'm going to do the O2 and the H plus. Becoming 2H2O. So here I have 0 charge, here I have plus 4, so I'm going to put the electrons on the more positive side, I'm going to put it here. So you can already tell that, okay, so it's going to be negative, number of electrons would be 4. That's N right here. And there are no units. Then I'm going to plug in Faraday's constant, which we saw to be 96,485, and I'm going to use J over V mole. $96,485 J over V moles. And all I have to do now is just get the cell potential of this. To do that, I have to look it up in the chart. So let's see, silver to silver plus 1. Let me see if it's in this table. So it's right here, right? It's positive 0.80 as a reduction, okay. So I'm going to write this here for now. So even though there are 4 electrons, you're not going to multiply this by 4 because it's an intrinsic property. So just use 0.80 volts. And then this one looks like water with O2 and 4H pluses. Find that here. Here you go. No, that's H2O2 right here. As written, it's positive 1.23. Positive 1.23. So it's positive 1.23 volts as written. So it's going to be, this is silver got oxidized. So this is the anode. Oxygen got reduced. So this is the cathode. So E cell is equal to E cat minus E anode. The cathode is positive 1.23 volts minus, this is 0.80 volts. And it's going to be 0.43 volts. And that number you plug into here, 0.43 volts. Okay, and so you cancel the V, you multiply that across, the free energy is going to be negative 170,000 J per moles of this reaction. And this is, or if you want in kilojoules, divide by 1,000. J 1 kJ. It's probably better to report it in kilojoules because it's so big. 170 kilojoules per mole. Okay, so that's how you get the delta G. On the next video, I'll teach you how to do the to find the K equilibrium.